Hi, I'm a light beam. You can call me Ray. Did you know that without me, you would not exist? I come from many different places. The sun and the stars in the universe, from fire, electric light bulbs, and many other sources of electric light. I can come from a candle, or even a match. In fact, it's because of me that you can see everything around you. If I didn't exist, everything would look like this. I can put on great shows, both beautiful and exciting. I work miracles and can make plants grow from the tiniest flower to the tallest tree. I am also faster than anything in the whole universe. I can reach the moon in less than 2 seconds. That's over 186,000 miles in a single second. Nothing is faster than I. At least, I think so. Now that you know how important I am, let me tell you how I work and all the things I can do. What your eyes see are actually many, many light rays, like me, that hit the surface of the object you are looking at and are reflected from it. Then the optical system of your eye forms an image from all the light rays. Reflection means bouncing back the light rays from the object they strike. Particles of dust, droplets of water, smoke can reflect me. On clear nights, the sky is black. There is nothing except the stars. Some surfaces reflect light better than others. The smoother and shinier, the better the surface reflects. A mirror is the best reflector of all. When I hit a surface and it reflects me, I follow a strict rule. It goes like this. The angle at which a light ray strikes a surface is the same as the angle at which it is reflected back. Scientists will say the angle of incidence equals the angle of reflection. I like that. It's easy to remember. Coming and going, I'll always be at the same angle. It's the same thing that happens when you bounce a ball against a wall. If you bounce it straight, it will come right back to you. If you bounce it at an angle, it will bounce, that is, be reflected at the same angle away from the wall. I can also flash messages by reflecting the rays of the sun with a mirror to someone far away. In the old days, before modern methods of signaling were invented, this kind of message flashing was often used. A device called a heliograph reflected the sun's rays, interrupting the reflections to make long and short flashes in code. You know, what you are doing now is a good example of reflected light. That's right, looking at a film. The light from the projector is shining through the film straight at the screen, creating moving forms that are reflected from the screen back to you. Making movies is one of my favorite hobbies. Have you ever noticed that when you look at something in the mirror, the image is reversed? This is fire truck number 7. If you look straight at it, the number 7 reads correctly. Now, when you turn and look at it through the rear view mirror of this rescue truck, the 7 is reversed. The mirror reflects what's in front of it. right becomes left, and left becomes right. Notice how the distance is reversed, too. You seem to be exactly as far behind the mirror as you really are in front of it. I've already told you that I travel faster than anything in the universe, even though some scientists now say there are things that go faster than light. I also travel in a straight line under most circumstances. However, when I pass from one substance to another of a different density, I change my direction. This is called refraction. You see, when I go through mediums such as water, glass, outer space, or the atmosphere, my speed varies a little. For example, when I travel through water or glass, I am slowed down. Here is a glass of water and a very straight pencil, just like me. Now, watch what happens when the pencil is put into the water at an angle other than 90 degrees. It seems to be broken where it enters the water, doesn't it? It doesn't look straight anymore. Well, that's because the light rays have been refracted. The same thing happens if the pencil is held behind the glass and seen through it. Look how it is broken up when it is moved to different positions. Here is what happens. This is a pane of glass. It will refract the light just as the water did. When a light ray passes through the air to the glass at an angle, it is slowed down and changes direction. When it goes back into the air, it speeds up and changes back again. It has been refracted. The size of the angle determines the amount of direction change or refraction. If the light strikes the glass at a 90-degree angle, it goes straight on through. There is no refraction. To understand why, imagine that instead of a light ray, I am an axle on two wheels, rolling along a hard, smooth surface, and coming to a strip of sand. The smooth surface is easy to roll on. It's like going through the air for a light ray. Coming to the sand at an angle, the wheel that hits it first is slowed down. The other wheel, which is still on the hard surface, keeps moving fast and pivots the axle to a new angle. The wheel that entered the sand first is also the first one out. As soon as it hits the hard surface, it begins to move faster, changing the direction to the original angle again. It is important to understand how refraction works. Many things use this principle to operate, such as microscopes, telescopes, eyeglasses, magnifying glasses, binoculars, cameras, and many other instruments. All of them use refraction by means of lenses. A lens is a transparent object that has at least one curved surface. They are usually made of glass, but can also be made of quartz or plastic. Lens surfaces are either concave, that is, sunken in like a cave in the side of a hill, or the opposite of concave, which is called convex. The flat plane on the side of each of these lenses give them the name of plano-convex or plano-concave. Many lenses are double convex or double concave. Most lenses, however, are convex on one side and concave on the other. They are called plus meniscus when they are thicker in the middle and minus meniscus when they are thicker around the edges. I can pass through all of them, of course, but remember, glass refracts me. When light passes through a lens, it follows another rule that goes like this. Light rays passing through a lens always bend toward the thicker part. See how these light rays are bent toward the thicker part in the middle when they go through the double convex lens. They come together or converge on the other side of the lens. This is what a convex lens does. Concentrating beams in a small area makes things very hot. A concave lens, however, is thicker around the edges. This is a double concave lens. Since all the light rays are bent toward the thicker part of the lens, they spread out on the other side. This is called diverging and is the effect of a concave lens. Lenses are commonly used in making eyeglasses. In normal eyes, the light rays enter the eyeball through the cornea and the lens and focus on the retina. Far-sighted people can see well at a distance, but have trouble focusing on close objects. Farsightedness may occur because the distance between the lens and the retina is shorter than normal. The image is blurred because the focal point is behind the retina. The correct convex lens brings the image onto the retina. Nearsighted people have the opposite problem. They can see well up close, but have difficulty focusing at a distance. This may be because the eyeball is relatively too long. The focal point is in front of the retina, again causing blurred vision. A concave lens moves the focal plane back to the retina, thus correcting the eyesight. Another kind of equipment that bends light is called a prism. Prisms refract light just like lenses, but they can do something else as well. You might say they are color producers. Let me explain what that means. Natural light comes from the stars, and the most important star for us, of course, is the sun. It gives us nearly all our natural light. Did someone say, what about the moon? Well, the moon, like any other reflecting surface, reflects light from the sun. Light also comes from many other sources, such as flashlights, fire, candles, and electric light bulbs. These different forms of light are called white light. White light is really made up of all the colors of the rainbow, which can be separated and produced by a prism so that you can see them. For instance, when a ray of sunlight strikes a prism just right, it is separated into all the colors of the rainbow. Here they are: red, orange, yellow, green, blue, indigo, and violet. There are many other things that can break up sunlight into colors. You know some of them. Soap bubbles can do it. And of course, drops of water. That's also how a rainbow is formed. Here is a disk spinning rapidly on an axle. What color do you think it is? Looks kind of off-white, doesn't it? Look at that. All the colors of the rainbow. Another example. three light beams, red, blue, and green, are projected against this screen. Where they overlap, it looks white. When a prism breaks down white light into all the different colors, this is called dispersion. The visible spectrum is the name of this row of colors shown by the prism. We can say that light is a form of radiant energy that travels in a wave motion. Other forms of radiant energy are radio waves and X-rays. All forms of radiant energy can be measured in wavelengths and frequencies. It's easy to understand what that means if you think of light or other energy traveling in waves, like the ripples on a pond when a stone is thrown into it. The number of waves that pass a certain point in 1 second is the frequency. The distance from the crest of one wave to the crest of the next is the wavelength. The colors in the spectrum have different wavelengths. The longest wavelength that we can see is red. The shortest is violet. This is the visible part of the spectrum. That's me. But I also have invisible neighbors. On my red side are the infrared rays, with wavelengths that are too long to be seen by the human eye. Beyond my violet side are the ultraviolet rays. These are too short to be seen, as are the very, very short X-rays. Infrared and ultraviolet rays, and of course X-rays, are well familiar to us. Infrared light can give heat. We cook with infrared. And ultraviolet light can cause sunburn. X-rays are very important to doctors. They let them actually see through the human body. There is another kind of light beam that is very special. It's called a laser beam. We already know that ordinary white light, such as a flashlight beam, is made up of many different colors, that is, different wavelengths. They travel in all directions independently. Such light is called incoherent light. Laser light, however, is of one wavelength with all the waves traveling in unison in one direction. In this way, they make each other stronger, and the laser beam is a very strong light beam indeed. The laser can produce the most intense light ever seen by man. It is so powerful that aimed against a brick, it can penetrate it in no time at all. It is so sensitive that pinpointed against the eye's retina, it can help perform the most delicate operations. Now you know a lot about me and all my friends and relatives. Didn't I tell you I was important? My job is done for now. I'm sure you'll remember everything I've told you. So, I'm off.